of our online course on fundamentals of smart grid sponsored by MIT. But what we realized that there are a couple of very good laboratory components because as you all know that this course is purely online. So few lab components which are already available to us. We thought we can make the course more interesting by sharing those lab videos for your references. But prior to moving to the video, let us, prior to moving to the laboratory component, let us discuss something about electric vehicle charging infrastructure and its importance. I think there are a couple of important things. Recently, we learned that the demand side management program, which is going to be quite exciting, and using microgrid or hybrid microgrid, such kind of energy deficit or peak energy deficit of the nation can be easily handled by having a control mechanism with all the microgrids of the nation. So what we are saying, you can manage the demand by instructing the consumers to move to another hour or by charging or discharging. But that can be, you can empower the control centers more if the microgrids are actually connected to a centralized control. Okay. So that is what the philosophy. But nevertheless, today almost considering the exponential growth of electric vehicles on the road today, which has touched more than 2 crores of electric vehicles on the road today, and it is expected to go as high as actually 5 crores in next couple of years. So one simple example, Manmohan, can you calculate 5 crore, 5 into 10 to the power 7 multiplied by 20 kilowatt? Okay? 5 into 10 to the power 7 into 20. So that is 10 to the power 9. That is going to be how many gigawatt? 1 gigawatt. Okay. So 1 gigawatt of actually the energy required, and the duration, the charging duration will be, let's say, 4 to 6 hours. Okay. So I can say 10 gigawatt of energy hour, 10 gigawatt of energy hour, I think will be a kilowatt hour, we can say. Okay. 20 gigawatt hour become, am I right? 1 into 1 gigawatt multiplied by, let's say, there are 5 to 10 hours. Okay. If they take at least 5 hours, so you can say 5 gigawatt hour of energy, 5 gigawatt hours of energy is required for meeting out the electric vehicle market. So what will happen actually, just imagine, and my load today is close to 200%, 200 gigawatt. So 5 gigawatt, or if I say at a particular hour, if it is going to be 1 gigawatt out of 200 gigawatt, so it is going to be close to 0.5 percentage of contribution. So what we are learning now, electric vehicle will contribute 0.5% of the peak energy requirement. Military. So today, if we are actually almost done with the energy, it may so happen because of the electric vehicle market, actually 0.5 to 1% of peak energy deficit may occur in this country, which is a very, very serious concern. A lot of hard work in last 10 years from 5% shortage to 0% shortage was possible. But either we have to add immediately 1 to 5% extra energy, or we have to experience a 0.5 to 1% energy deficit. So that is what the story is. So what we need to do, we have to make sure that the electric vehicle management, charging infrastructure management is one aspect. But to accommodate those 5 crore electric vehicles in next 5 years on road, how many charging stations we require? One charging station even accommodate, let's say, 4 to 5. Still, we need actually millions of charging stations required for this country to manage the electric vehicle charging infrastructure. Am I right? So it is one thing is clear that millions of electric vehicle charging stations and their optimal operation to avoid peak energy deficit become mandatory. Now, the second phase is quite important. This is about the grid side. But when you talk about 5 CR electric vehicles or 2 CR electric vehicles, means 2 CR batteries. Okay, either you have an onboard charging or off-board, you have a 1 to 2 CR batteries, and those batteries actually need to be replaced, need to be managed. So one important part of battery life is about battery management system. So if you do not have a proper battery management system, especially indigenous, so there is a huge market. Electric vehicle is anyway, we are dependent on somebody else. But if you are not having a proper battery system, then the maintenance also will go outside India. The batteries need to be replaced, which you do not want to do it because this become a junk. We need to make sure the life of the battery are reasonably higher. And to do that, until unless you have a balance between the cells, probably the battery life cannot be maintained properly. So battery management system and electric vehicle charging infrastructure, these two are actually very, very mandatory. Now, coming back to electric vehicle, when we talk about vehicles, I mean, they start from actually two-wheelers to four-wheelers to, I mean, three-wheelers, two-wheelers, three-wheelers, four-wheelers, as well as trucks and buses. So now the market, if you're really looking for the green energy and electric vehicles, it is not limited to four-wheelers. It is not limited to four-wheelers, but it is more or less depends on large, heavy vehicles, which is almost as good as 10 cars, 15 cars, 20 cars. So one truck will evacuate all your energy. So that is an important aspect actually. How do we have charging infrastructure, which are not only charging a single vehicle, but either charging actually 20 vehicles, in parallel, or able to charge one bus, one truck in parallel. So that is what the future mission. So the charging stations are no more, 20 kilowatt or 50 kilowatt. It become 200 kilowatt, 500 kilowatt capacity. It's a big stations. Then that is not enough again because, sorry, mm, uh, yeah. So one more important part about the renewable energy integration. So when you talk about electric vehicle charging, so it is responsibility of the charging station to evacuate the power with whatever little available through renewable, utilize them, and if necessary, then you draw from the grid. So renewable integrated electric vehicle charging station, renewable integrated electric vehicle charging station become the future. Okay. So, and then now when I say you can do DSM using DC microgrids or AC microgrids or hybrid microgrids, I can also perform actually DSM or demand response activity using those huge charging stations. Got it? Is it fine? So that's excellent. So, and hence let us, I'll hand it over to Manmohan to run the videos, please. Go ahead.
Very good morning. Welcome to the course on Smart Grid, Basics to Advanced Technologies. And we are going to discuss on battery management system today. The main functions of battery management system, that is so called BMS, are monitoring the current through the circuit, cell voltages and ambient temperature, estimation of key states such as SOC, SOH and SOP using online estimation techniques. Cell balancing to balance the voltage or SOCs using active or passive components, computing the energy and power limitation of the pack using estimated SOC and SOH values. However, in this lecture, our contributions are confined to the demonstration of cell balancing techniques only. A detailed description of other functions is provided in the previous BMS lecture. Generally, the health of the lithium ion batteries will be degraded after some cycles of usage. This poses differences in their capacity and results in a decrease in their efficiency. The weak cell in the module charges and discharges faster compared to other cells. To mitigate these issues, balancing of cells are necessary, and it allows the batteries to look alike in capacities and increase the efficiency of the cells in a given module. Cell imbalance can be categorized majorly in two types. First one temporary and the second one is permanent. The temporary causes of cell imbalance include uneven distribution of leakage and self discharge currents. The difference in Coulombic efficiency, which is a minor imbalance, performance or operation, and uneven temperature distribution. Assuming that all the cells have the same composition, the Coulombic efficiency, performance or operation, and self discharge will be the same, leaving the most significant imbalance factor, uneven temperature distribution and leakage currents, current distributed to the BMS. The permanent causes of cell imbalance include internal resistance change, self discharge rate, damage to static electrolyte interface, and capacity differences. If this continues, the weak capacity cell will gradually deteriorate prematurely than others. Imagine a case where a less capacity cell and fully capacity cell are connected to a load, it will neither discharge nor charge. A detailed discussion on the importance of requiring a balancing circuit in the BMS is provided in the theoretical lecture on the BMS, that is battery management system. Kindly refer to the lecture for more detailed information. There are many cell balancing methods. Cell balancing is broadly divided into two methods, passive and active methods. The passive methods are segmented into overcharge and shunt resistor methods. The active balancing methods are segmented into cell to cell, cell bypass and pack to pack balancing. The basic balancing required for a module is cell to cell balancing, also called cell balancer. This cell balancing is again subdivided into adjacent cell to cell, any cell to any cell and direct cell to cell balancing. Let us consider the passive balancing system. This experiment aims to demonstrate a simple passive balancing for the charging and discharging operation of 3 lithium ion batteries through a readily available balancer IC. The bleeding register present in the ICs allows the charge of the higher capacity cell to deplete through this register for both charging and discharging operations. The components required for this experiment are 3 18650 lithium ion cells, a readily available passive balancer IC, a DC power supply for charging operation, a rheostat for discharging operation. Let us get into the component specifications and their importance in this experiment. 3 18650 lithium ion cells of 3000 milliampere hour capacity with a nominal voltage of 3.7 volt each are used in this experimentation. The lithium ion cells are connected in series combination to make up to 11.1 volt. The passive balancer IC with specifications as 3S 20 ampere and 12.6 volt maximum, it can handle 20 ampere of current and have protection for short circuit, overload, discharge and overcharge, which provide safety and protection for the lithium ion batteries. A DC power supply is used to charge the battery and a rheostat of 20 ohms for discharging operations. You can see the passive balancer IC. The connection diagram consists of 3 positive connections from the battery and 1 negative terminal connection, and a pair of positive and negative is provided for the external connection, which is for the charging and discharging connections. Now, the detailed architecture of passive cell balancing has been presented before you. This is the schematic of the balancer IC, which consists of 4 N channel 85N3L switching MOSFETs, DW01 overcharging and over discharging protection IC, G1 SMD NPN high voltage transistors, 2L PNP high voltage transistor, 1 port charging and discharging terminal and few resistors and capacitors. After connecting the batteries to the balancer IC, we are going to check the balancing operation for both charging and discharging using the DC power supply and rheostat respectively. Let us observe charging operation. The battery module is charged by the DC power supply and the path of the charging goes through the DW01 protection IC and through that switching MOSFETs 1 and 2. Once the battery reaches its limit, the switching MOSFET activates and the current takes the resistive path until all the cells come to the same voltage. One of the thyrocell voltage or peak charge voltage 4.2 volt is reached, the protection IC activates and stop the charging operation of the battery module. Similarly, we can also see the discharging operation. In case of similar to the charging operation, the current passes through DW01 protection IC and through switching MOSFETs 3 and 4. Once the battery module reaches the cutoff voltage of 2.4 volt, the switching MOSFET activates and depletes the charge of other batteries until all the cells reach cutoff voltages. Similar to the charging operation, the DW01 activates once all the cells voltages reaches cutoff voltages. As we can see from the DC power supply display panel, we can see that 12.6 volt is appearing across the terminals of the balancer IC. With a current of 1 ampere and a wattage of 12.6 watt of power is storing in the batteries. Since the battery current takes the resistive path for balancing, heat is generated inside the module, which leads to deterioration in the battery capacity and may even cause thermal runaway. In this regard, even though passive balancing is easy to implement and has less cost comparatively, it is not recommended for large modules because of frequent failures. Moving to active balancing, in this experiment, we aim to demonstrate how an active balancing mechanism works by utilizing TMS 320F28379D as a controller and Opal RT as a plant. To perform active balancing, one should determine 3 major factors: mode of charge distribution, for example, direct cell to cell, adjacent cell to cell, energy sharing, balancing topology, that is type of converter, boost, buck, flyback, half bridge, and third is balancing strategy, that is what type of control logic parameters need take care of, example voltage, OCV, SOC and SOH. Now, this is what generally the CHIL setup look like, and in due course of time I will be explaining you the complete operation of CHIL setup. Now, first of all, what is a CHIL experimentation? The controller hardware in the loop system allows the verification of the proposed control logic provided in a real time controller in conjugation with the plant, which is running at a very fast time scale either in real hardware or controller. Thereby, any changes in the control logic in the real time should be governed and processed by the fast acting plant. The components required for this experiment are a TMS 320F28379D launch pad and an Opal RT controller and a simple PC. In this experimentation, the charge distribution considered here is energy sharing, and balancing topology is a boost buck converter, and the balancing strategy is based on SOC. This is the schematic of CHIL experimentation. The working of CHIL is shown in this diagram. Firstly, the TMS board is equipped with ADCs and EPWM pins. The input will be provided from the OPLRT, which is taken here as a plan to the ADC of the TMS board and is utilized for the control logic development. By utilizing MATLAB, the control logic is developed, and through hardware simulation, the developed code in MATLAB is flashed into the TMS board. The necessary parameters will be called out into the console to verify the control logic for various parameters. The EPWM terminal pins present in the TMS board generates PWM pulses, which are connected to the OPLRT through digital input pins provided to it to drive the converters. Let us discuss the construction of CHIL setup in the following steps. Step number 1, consider a battery system of 3 modules, so called plant in OPLRT. Step number 2, call out the necessary parameters required for balancing strategy from the plant. Step number 3, develop a balancing code in MATLAB using the called out battery system parameters. Step number 4, do the necessary connections, that is, the parameters from the OPLRT analog out pins to ADCs of the TMS board with proper scaling. The PWM pulses from TMS board EPWM pins to digital out pins of OPLRT to drive the converter sitting in the plant. Now, we can look into the complete block diagram of the battery system within OPLRT. This is the block diagram of the battery storage system connected to a DC bus, and from the diagram we can observe that the 3 battery modules connected to a load or charger, each module consists of a CMB known as cell management block, which consists of cells connected in a series parallel combination with a balancer circuit. The driving circuit, which takes input from TMS, drives the MOSFETs. Let us discuss the working principle of the battery system. The system consists of 3 modules and a boost buck converter, each to step up or step down the battery voltages as per the requirement. Such a mechanism is called energy sharing because each module can be controlled individually, which resembles the sharing of the power demand accordingly. If the duty cycle D of all the converters are same, then all the batteries share power equally. By using this concept or mechanism, we have developed a control logic that provides duty cycle D based on the variations in SOC values of the battery system. A TMS board is equipped to generate the desired PWM signals. The TMS board, which takes the input from the Opal RT currents SOCs and power demand PD, generates D1, D2, D3 duty cycles based on the algorithm flashed into the microcontroller. The parameters of the storage system are presented in the table as shown. The initial SOCs are taken as SOC 1, which is 65%, SOC 2 62%, and the SOC 3 70% respectively. The average SOC is close to 65.66. The nominal voltage for 3 modules is 48 volts. The capacity of modules is taken as 5 ampere hour each, and initial DC voltage is 270 volts. Initial power demand is 1000 watts. The converter parameters as inductance of 5000 microhenries, the capacitance of 200 microfarads with switching frequency of 5 kilohertz. This is the back panel of Opal RT, where we can see multiple groups. The group 1 consists of analog in and analog out. Group 2 consists of digital in and digital out. As we can see, for our experiment purpose, we have used 7 analog out signals with a ground pin and 3 digital in signals with a ground pin connected through a DB37 channel. After setting up the connections as per the block diagram, let us understand the simulation platform of both Opal RT and TMS board. Firstly, the required MATLAB installations for the TMS board need to be done. Also, the control suite for the C2000 microcontroller is required, which provides libraries at every stage of development and evaluation. After the installation, MATLAB provides hardware libraries for the TMS board. In this experimentation, we have taken 7 parameters as an output from Opal RT analog out for control algorithm. The parameters are input battery currents, SOCs of 3 batteries, also the power demand PD. All the 7 parameters are scaled down to 3 volt at Opal RT itself, because the TMS board runs on 3.3 volt only. Any higher voltage might damage the board. 7 ADC blocks are taken for the 7 input parameters. 3 battery currents are compared with reference currents generated from the algorithm. The SOC balancing algorithm is developed based on the average standard deviations. By comparing the SOC values with the mean values, a balancing factor is determined for all the 3 batteries in a similar way. Using the balancing factor, the power is shared among the battery module accordingly. By using a PI controller, the voltage bus is maintained and also develops PWM signals. These 3 signals are sent to the Opal RT through digital input pins for 3 converters presented in the plant. The Opal RT plant model, which consists of 3 battery modules and 3 converters that are connected to a common DC bus with a power demand of PD. Now, let us focus on its operation. To evaluate the proposed control algorithm, experimentation using a built-in MATLAB equivalent circuit model is developed. The simulated model consists of 3 battery modules, and each module is connected to a bidirectional DC-DC boost buck converter for discharge and charge operation according to the reference current provided to it from the control algorithm. The converter consists of an inductor of 5000 microhenry and a filter capacitor of 200 microfarads. The battery nominal voltage taken here is 48 volt for each module. Now, if you focus on discharging operation, the individual battery currents is presented in the DSO at the first 3 channels and SOC values in the next 3 channels and power demand PD in the 7th channel respectively. Now, let us focus on the variations in load demand. To examine the control algorithm for load power variation, load power changes are applied to the batteries during discharging operation. Initially, the power demand is kept at 1000 watt and a gradual increase of power by 200 watt is applied till the power demand reaches 2000 watt. We can observe the input current of batteries in the first 3 channels of DSO. Also the SOC values are draining faster than the earlier. From this, we can understand that the algorithm takes the power demand changes without any setbacks. Variation in bus voltages. In general, the DC bus voltage from the energy storage should be always maintained irrespective of changes in battery voltages. Let us observe how the V bus changes are taken care by the proposed control algorithms. The initial DC bus voltage is taken as 270 volt and then it is changed to 300 volt and 260 volt respectively. It can be observed from the DSO the change in DC bus voltage does not affect the battery voltages or currents and the DC bus is perfectly regulated. Variation in SOC values. Let us change the SOC values to 75, 73 and 65 respectively compared to the previous values for all the 3 modules and observe its effect. From the DSO, we can observe that the change in SOC is proportional to the currents of the battery, which validates that the proposed algorithm is working exceptionally well to cater to all the changes. In this lecture, we have learned the 2 popular balancing techniques, that is passive and active balancing, how to develop a control logic using a low cost TMS board, understanding of how to develop and work on a CHIL setup for a balancing mechanism. I hope and confident that this lecture drives you to work and develop balancing mechanism for various topologies and balancing strategies of batteries in future. Thank you.
dear students, I mean, you see, please go through the videos very smoothly and because, the way it has been described almost like, this is the best way it can be, anything can be explained. So if you see, this is a very small thing, but actually when you really work on a problem, today I think it is very, very rare in this country, researchers working in balancing mechanism. Everyone work on actually, use converter inverter mechanisms or control strategies or even the developing controllers. Uh, Very rarely students work on BMS because the battery technology, uh, which has not emerged as good as we desired as of now. So because we normally buy and do it, use it, once it is done, we throw it. But probably the maintenance of electric vehicles, each and every technician of any electric vehicle company must know how to balance it properly. Am I right? So I think we'll move to the charging infrastructure very soon. Over to you.
Very good morning, dear student friends. Welcome you to the topic on EV charging system of the course titled Smart Grid Basics to Advanced Technologies. The EV charging infrastructure, as you could see, which has been taken out of the source available at Niti Aayog, and most likely, as you could see, there are two different type of charging concept. One is from AC, the other is DC, and the e-vehicles or so-called e-mobility expected to be one of the serious loading to our electric network in future. As of now, the four-wheelers of e-mobility, though it has shown its presence in this country, but it is not so significant. However, the three-wheelers are almost reached more than 2.5 to 3 crores as of now. So country like ours, electric vehicles, especially two-wheelers, three-wheelers and four-wheelers, are going to play a major role as well as a concern to Indian power system in future. Electric vehicles are always charged with DC. If the input is AC, then a conversion stage is required to convert AC to DC. And mostly it is from AC to DC because of residential charging or parking systems. There are four modes of EV charging operation. The mode 1 consists of a direct connection from a socket to the EV without any special safety. Typically, mode 1 is used for charging electric bikes and scooters. The mode 2 of charging scheme requires a specific safety system between the point of connection to the electric network and the car in charge. The system is placed on the charging cable and is called the control box. It is installed on portable chargers of electric vehicles. This can be used in public as well as in domestic sockets. The next mode of operation, mode 3, requires an EV-SE equipment to charge the electric vehicles, which is permanently connected to the electrical network. Moreover, the control box is inherently integrated into the EV-SE. Wall boxes commercial charging points, and all automatic charging system comes under this mode of charging. Mode 4 offers DC supply directly to the electric vehicles. This requires a current converter external to the vehicle that connects the charging cable. In the figure, we can observe the AC charging modes are all on the left side to you and the DC on the right side with the socket pins. The AC charger ranges from 2 kilowatt to 22 kilowatts, and the DC chargers range from 2 kilowatt to more than 200 kilowatts. Now you can see different models of DC charging plugs from Tesla and many other manufacturers. USA and Japan have Type 1 AC and Type 4 CHAdeMO DC, Combo 1 AC-DC, and Tesla's proprietary AC connector. Europe has Type 2 AC, Type 3 AC, Type 4 CHAdeMO DC and Combo 2 AC-DC. China has Type 2 based AC and its own DC GBT connector. With respect to car manufacturers, Americans, Europeans, Koreans car manufacturers have adopted CCS combo, and Japanese car manufacturers have adopted CHAdeMO. As the number of EVs is growing day by day, the adoption of new technology has seen exponentially growth. Hence, the stated charging connector list is indicative and will get changed over a period of time. Now, the architecture of EV charging system, where you could see there are multi-stage charging mechanism for electric vehicles. The architecture followed in India is EV connected to EVSE, which is monitored by CMS by user application. EVSE, electric vehicle supply equipment, which connects the charger to the main electrical supply. It also offers authentication, metering, payment services, and remote monitoring. Bureau of Indian Standard (BIS) has published standards IS 17017 that covers the general requirements and safety norms for EVSEs. Charging protocol defines the type of connector that goes into the vehicle inlet, max power and voltage for connection, communication protocol, and the type of communication links. Now, next is CMS, which is Central Management System, is a cloud-based platform managed by the company operating the charging station. The EVSE communicate with the CMS to manage the user authentication or authorization, billing and rate of charging. It also enables user-defined apps to help end users to identify the nearest charging station and also reserve a charging slot and pay. Now, the smart charging concept for optimal electric vehicle integration and its advantage of smart charging. For utility distribution network operators, it helps in more hosting capacity, faster implementation, and less cost. For utility transmission system operators, it extends the limitation in system peak load and avoids the construction of additional generation capacities. For building managers, time of use tariff optimization, PV balancing optimization, demand charge management and demand limitation, load balancing and reduction of the connection fee. Now, considering the EV charging system in this country, because the manufacturers are many, so it is equally important to have EV charging standards. Now, you can see different elements and their standard type and components of different EV charging equipments or devices. This slide presents the essential charging components and their standards. The charging interface, which includes plugs, sockets, vehicle couplers, follows IEC 62196-1/2/3. The communication protocol, that is V2G/data link layer and physical signaling process, ISO 15118-1/2/3 and ISO 11898-2. The EV conductive system follow IEC 61851-1/21/22/23/24. The battery swapping follow IEC 62840. The conductive charging connection set possess GB/T 20234-1/2/3. China and the information technology safety equipments have IEC 60950-1. In our laboratory, we have a DC fast charger type 2, which is VEVC001. Generally, the DC fast charger with high power operation, the AC-DC converter, DC-DC converter and the power control circuits become larger and more expensive to keep in an onboard charger. This necessitates the implementation of an off-board charger so that it does not take up space within the vehicle, and the DC fast chargers can also be shared by many users. As we can see in the schematic, the input voltage is 415 volt AC supply. In the first step, the alternating current or AC power provided by the AC grid is converted into direct current or DC power using a rectifier inside the DC charging station. Then the power control unit appropriately adjusts the voltage and current of the DC-DC converter inside the charging station to control the variable DC power delivered to charge the battery. There are safety interlock and protection circuits used to de-energize the EV connector and to stop the charging process whenever there is a fault condition or an improper connection between the EV and the charger. The battery management system or BMS plays the key role of communicating with the charging station to control the voltage and current delivered to the battery and to operate the protection circuit in case of an unsafe situation. So, this is the input coming from three-phase AC supply, which is a 5-wire system with 3 phases, including one neutral and one ground. This is the auxiliary battery system to operate the components in the charger. We can see that it is guarded by an MCB. From the MCB, it proceeds to the power conversion system, that is rectification and DC-DC conversion. This is the control unit that controls the charging and communicate with the BMS whenever any fault in charging. The control unit send the signal to the BMS to cease the charging process completely. This EV charger works on GB/T 20234.3 protocol BVC001 model, the rated input current is 25 ampere. The output voltage is 48/60/72 volt DC and 200 ampere maximum, and the load capacity is 15 kilowatt maximum. Now, the issues related to fast charging. Fast charging is quite attractive in the sense of high power charging with short duration of time or short charging times. But the fast charging power cannot be increased infinitely. That is due to 5 technical limitations. First one, higher charging current leads to higher overall losses both in the charger as well as in the battery. As the charging current increases, the effective capacity of the battery decreases as well. For example, as given in the Peugeot's law. The second one, the battery C rate increases with fast charging, and this reduces the battery lifetime due to the heat produced and increased degradation due to the higher temperature. Point number 3, when fast charging takes place within a battery, the SOC of the battery can only be reached till 70 to 80% and maybe a little bit more like 85 to 90%. But this is because fast charging create a lag between the voltage and state of charge SOC, and this phenomena increases as the battery is being charged faster. Hence, fast charging is typically done in the constant current or CC region of the battery charging, and after that the charging power is reduced in the constant voltage or CV charging, that is the constant voltage charging. For any EV charger, it is important that the cable is flexible and lightweight, and for people to use and connect it to the car. With higher charging power, thicker cables are needed to allow more charging current. It is very simple. I mean, if you like to, the resistance which decides your uh, diameter of the conductor, and based on the required power, if you like to push maximum, then probably the size of the cable need to be increased. Else it will heat up due to the losses. In the future, with currents above 250 ampere, the charging cable should become heavy and less flexible because they are so thick, so you perhaps cannot fold it as you wish as so, and this is not comfortable to use at all. The solution would be to use thinner cables with cooling and thermal management to ensure that cables don't heat up quickly. That is, of course, more complex and costly than using a cable without cooling system. Now, coming to an end, to conclude in this lecture, we have learned that different types of EV charging systems available, different standards for electric vehicle charging, and its architecture followed in India based on different manufacturers across the globe. A practical demo of the components involved, its architecture and working of EV charging system is also being understood in its basic form. I hope this lecture has brushed the basics of EV charging systems, but once again I request all of you to read more literature to understand more about electric vehicle charging mechanism for better understanding. Thank you very much.
Thank you very much. And probably, uh, I mean, you see, electric vehicle charging and the battery management system As I told you, it is not too common to most of the laboratories, but this is a very interesting area. If you like to make career in this field, so probably you have to really, work on a field or a lab where you have either a charger or you must have developed a charger, okay? So I think this is not a very difficult task, especially for power electronics engineers, because the concept is simpler, but slightly laboratory level actually risk is associated because, a lot of on-off things you need to do. It's not like do with a low voltage capacity, at least for 5 kilowatt, 10 kilowatt charging, you require a lot of safety concern is very, very important. Otherwise, rest things are fine. But if you have any questions, I'll be happy to defend, dear friends. Just you can introduce yourself, and if you have any questions related to not only today, but yesterday and today. Okay, if you have read something yesterday, if you have felt that something need to be clarified, you can ask. Yesterday's lecture and today's lecture. Please. Or because, it has been taught very smoothly and nicely, so you may be thinking that there is no doubt. But still, I'll be happy if you ask anything that you read yesterday. Anyone could read something yesterday, or you simply gone to bed after the lecture? Anyone who could? Avinash, how are you? Deepa Jain, Muthu Selvan, how are you all? Hope you all are doing well. Chandrasekhar,
All of you are now admin. You can unmute yourself and
yes, Bangar, yes, sir, you're doing well. Soumya, am I right?
so you can communicate with sir.
I think they all are fine, but not asking question. Okay. Anyone? Yeah. Don't
Good evening, sir.
be scared of asking question, please.
Sir, good
I
evening,
think
sir.
someone is asking.
Sir, this is Narendra, sir. Good evening,
Devendra
sir.
Singh,
Good evening, sir. Am I audible, sir?
I think when you are scheduling the examination, the quiz test,
Tomorrow evening we will.
tomorrow, what time?
Sir, it's online only. We will float on Canva, so they can attend anytime whenever they are. We have
So tomorrow after the lecture we'll launch. So the weekend actually they can do it.
once
How?
they start, they have to finish in 30 minutes.
Yeah, we'll explain to them. So I think tomorrow evening after the class, we'll offer you a quiz test, and the process of answering or appearing in the quiz will be explained by Dr. Manmohan tomorrow at around 6:30 p.m. And I hope actually it seems they're all comfortable. Okay. So with this, we come to an end of today's lecture. Thank you very much.
Good
Take
evening,
care
sir.
and bye-bye for the day.
Sir, good evening, sir.